Okay, let's talk about decoupling or turning this second order into a system of first order. So we're given the substitutions to make here. So here, I'll put that here. That is question number 5. U double prime plus 3u prime minus u equals e to the 4t. So if we let x be u and y be u prime, then my first equation, x prime, would be u prime, just taking the derivative there. But u prime already has a name, that's y. So there's my first dE, x prime equals y. Okay, then what about y prime? Y prime would be u double prime, right here, just taking that guy's derivative. But I know what u double prime is. If I solve the main equation for u double prime, I get negative 3u prime minus u, or plus u, going to the other side, plus e to the 4t. These two guys already have names in terms of x and y. Remember, we're just converting everybody into x and y. U prime was y, and u was x. So that means my second equation, y prime, will be x minus 3y plus e to the 4t. And that's exactly what we get here. Okay, this one's kind of taking that idea and going backwards. Now, I would have to really think about matrix theory and why this works for this particular system. But I'm 99% sure the reason we can convert this first order system of DEs into a single second order DE is because this matrix here has a determinant of 0. If you notice, if I multiply the first equation or the first line, the row, by what do I want? Negative 5/3, I get the second one. So my determinant there is 0. I think that's what will allow us to just write everything in terms of x. So, like, I know I haven't done any examples like this because this doesn't come up that often. So this is just going to be a homework problem. You won't have a problem like this on the test. You will have a problem like that on the test. Okay, so I went ahead and worked through it here. So here is our system of DEs here. So if we just go across our top row here, x prime will be negative 3x plus 3 times y. Y prime will be 5x minus 5y. I'm just multiplying out the matrix times this vector and then setting each equation, each row equal. So this is top line, call that number 1. Here's the bottom line, number 2. Okay, I know I want this in terms of x double prime, so I just went ahead and took the derivative of everybody here. So I'll get an x double prime minus 3x prime minus 3y prime, derivative of 0 is 0. All the derivatives are with respect to t here, by the way. Okay, this equation, by the way, can be rewritten like this. If I wanted to solve this guy for y in terms of x and x prime, I'd get this guy right here. So we're going to need this in a minute. Okay, the second equation is y prime is 5x minus 5y. So we can take that and stick it in right here. I'm just trying to eliminate all the y's. That's all we're doing here. Is really this is just an elimination problem. We're trying to eliminate all the y's. Okay, so plugging that in here, we get this. So just distribute the 3. Now the problem is I still got a y left. I've got almost all the y's gone. There's still one y left right there. So I'm going to take that thing and plug it in. And then all we have left are x's. By chance, it's x prime. These two canceled out. That's just coincidence. I don't know if that's going to happen every time. Okay, so here's what we get. Here's our second order DE that only has x in it. And then that may be easier to solve. We could find our characteristic polynomial and so forth. And like we're really good at solving these. And you can see here that's the correct answer. Okay, let's take a look at number 7 because it's just nasty. So it's x1 prime. You know, I'm going to write this in matrix form. Plus 830, not plus, I won't have a plus there. I'm writing this in matrix form. 832, negative 320, negative 517. And that'll be multiplied times the vector x1, x2. And then let me go ahead and write down my initial conditions. X1 of 0 equals 24. X2 of 0 equals negative 15. Okay, so let's get this set up. Let's get our characteristic polynomial here. Let's set up our determinant equation. We want the determinant of 515 minus lambda, 832, negative 320, negative 517 minus lambda to equal 0. Now, let me make sure I copied all those right before I get too far in this. 515, 832, 320. All right. Okay, so then multiplying, remember we go like this minus like this. So 515 minus x times negative 517, that's a lambda. Minus, that minus is going to cancel that negative, so it's going to be plus 320 times 832 equals 0. I am not going to sit here and try to solve this by hand with all these nasty numbers. I would now just take this and go to Wolfram Alpha. And just type it in, 515 minus. And I'm going to call it x for the purposes of typing this out because Wolfram Alpha will be happier with that. Negative 517 minus x plus, and it was 320 times 832 equals 0. And we get nice, pretty answers. That's very reassuring that we get nice, pretty answers. Maybe we could have just multiplied that out by hand and a whole bunch of stuff would cancel. But no, I'm not going to. We get negative 5 and 3. All right, so our two solutions are lambda equals negative 5 and 3. Then that means x1 is C1. Oh, we got to find our eigenvectors now. Yeah, let's find our eigenvectors. Okay, so let's do lambda equals 3 first. Remember, there are two different ways to find an eigenvector. You can do A times K equals lambda K, or you can do A minus lambda I where I is the identity matrix, times K equals the 0 vector. I find this second one easier. That way I have the same thing when I get my system of equations, I get 0 on the right-hand side for both. So I just find this version easier. So I'm going to do that one. So that will be, I'm doing literally this same matrix right here where I'm plugging in the lambda. So that'll be, let's see, 512, 515 minus 3, 832, negative 320, negative 520, negative 517 minus 3. This is a matrix now. This is not a determinant. Times the vector, K1, K2, equals the vector 0, 0. And here we get 512 K1 plus 832 K2 equals 0. Just take this row times this column, and that will equal this element. So that means 512 K1 equals negative 832 K2. So K1 is negative 832 over 512, assuming all my arithmetic is correct. Let's see what that is. Let's see, which way was it? 832 over 512. My guess is that reduces to something pretty. I don't know why that's not loading. (29 over 19), and it's negative. So K1 equals negative 20. I already lost it. 29 over 19. So the way my mind works is I like to swap coefficients. So I would bring this 19 back over here. 19K1 is negative 29K2. So then just swap coefficients, and I would have negative 29, 19. That would be my vector K. Okay, I'm curious if I say we won't know until we plug in the initial conditions. Looks like one of our C's is going to be 0 here. So, okay, then I guess if we're going to really check this, we're going to find the other eigenvector. So now we'll have, I need to come down here. Let's do lambda equals negative 5. So I want 515 minus negative 5. That'll be 520. 832. Negative 320. And then, oh, well, we got a lot of negatives here. Negative 517 minus a negative, so plus 5. So that'll be 512, negative 512. Okay. By the way, a good way to check and see if we got this right here, we could actually check this here. This second row times this vector should give us the same equation. So up here, we could have also done negative 320 K1 minus 520 K2 equals 0. So that's negative 320 K1 equals 520 K2. So K1 is 520 negative over 320. If that's a different fraction than what I got right there, then I've done goofed somewhere. So 520 over 320. (13 over 8). Yeah, so that means there may be a mistake in here. Let me pause and see if I can find it. Yeah, see, it's a good thing I checked. I must have typed it in wrong the first time. 532 over 512 is 13 over 8. So this was wrong. This should have been negative 13 over 8. So remember, when you're finding the eigenvector, one row should be a multiple of the other. These two equations should give you exactly the same thing. So we don't have to solve both. It's not really a system of equations we're solving, because any multiple of an eigenvector is still an eigenvector. We don't solve for K1 and K2. We find values for K1 and K2 that satisfy this. So you get one equation from the top and one equation from the bottom. You use either one, but it's good to check both to make sure you haven't done goofed like I did. So this should have been 13 over 8. Negative, of course. Oh, so now I got to fix all of this. So then again, I just swap the coefficients. Negative 13, 8 is my eigenvector. And I get the same thing here. Okay, and then plugging in negative 5, we'll get 520 times K1, K2 equals 0, 0. Okay, so this is my first eigenvector here. I'm going to find my second eigenvector now. You may have a problem with me reusing the letters K1 and K2 since I've already used those. If you want to use different numbers here and call these little coefficients of our vector 3 and 4, that's perfectly fine. But it's pretty standard to do this. Like most mathematicians will write this up the same way. We found one eigenvector. The algebra to find the eigenvector is done. So these little parameters here, these variables that I'm using here, these were just dummy variables I was using to find that vector. Now I'm free to reuse those letters again. So this would be 520 K1 equals negative 832 K2. And again, I would like to reduce that, and I just think it's going to be easier. We could just use the numbers the way they are. We just type that in, get that as a reduced fraction. Is that 832 over 520? Eight fifths. So K1 is negative 8 fifths, K2. And I could do this. I could say, okay, well, I'm going to let K2 be 1. Then K1 is negative 8 fifths times 1. Perfectly fine. I don't want to have to deal with the extra fractions in there, though. So I would bring the 5 back over and then swap coefficients. So if I let this guy be 8 and that guy be negative 5, both sides are going to equal positive 40. So this guy is going to equal that. That guy is going to equal that. So K1 was negative 8. K2 was 5. And this is, when I say K2 here, I mean eigenvector 2. This is the vector. Or like maybe I want to put the negative on the bottom. Or I could do this. Once we solve the initial value conditions, all these different ways I could write these eigenvectors, it'll all wash out in the end. It doesn't matter. We'll still get the same initial value solution. So any multiple of an eigenvector is still an eigenvector. I can make this 80 over negative 50, still work. All right, then x1 will be C1 here, let me write it in matrix form. It's easier for me to write it out to begin with in matrix form. The vector x is C1 K1 negative 13, 8 times his e to his eigenvalue t plus C2 K2 8 negative 5 e to his eigenvalue t. There is my general solution. Now I have to solve the IVP. So I'll rewrite those here. Let's write out each variable first. X1 will be just going across the top. That is not a fraction. I have a habit of making my eigenvectors fractions. That eigenvector is not a fraction. That's a 2 by 1 matrix. Okay, so we go across the top for x1. Negative 13 C1 e to the 3t plus 8 C2 e to the negative 5t, and then go across the bottom for x2. So that'll be 8 C1 e to the 3t plus 5 C2 e to the negative 5t. And you may be thinking, well, 5C2, isn't that just some new constant? No, you can't do that with these coefficients here in front. Remember, it's a system we're trying to solve. So you can't go, well, 8 C2, that's a new C2. You can't absorb these numbers in front of the constants into the constant. We're trying to find C1 and C2 that will make these equations satisfy the initial values. And I don't remember what those were. 24 and negative 15. It's x1, x2 0 was negative 15. Okay, and then again, like we get some nasty system here. I mean, I guess we can write it all out. Negative 13 C1 e to the 0 is just 1 plus 8 C2 e to the 0 is 1 equals 24. And then from the second one, 8 C1 plus 5 C2 equals negative 15. There's my system of equations. If it were easy, if I could do it easily doing elimination or a real simple substitution, I would solve it by hand. I'm not going to solve this one by hand, especially not right here in front of you. I type it in Wolfram Alpha. And just so I don't confuse it, I'm going to use the variables x and y for C1 and C2. Negative 13x plus 8y equals 24, I think is the first one. And 8, 5, negative 15, comma, 8x plus 5y equals negative 15. Okay, did I type everything right? No, I did not type everything right. There's a negative right there that I did not have here. I just couldn't read my negative here. And I know it's not right because I can see the answer has C1 equals 0, or one of the C's is 0. So this should be a minus right there. Okay, so let's fix that. Right there, minus. And we get x equals 0, y equals 3. So C1 is 0, C2 is 3. So then both of these guys are 0 right here. Both of those are 3. And just for completeness, I'll write this up here. Let's see if C2 is 3. I'll get 24e to the negative 5t. And x2 will be, what is that, negative 15 e to the negative 5t. Which is exactly the right answer. Okay, so on a test, I would not give you a matrix this nasty with numbers that big. But all the steps I took, it's perfectly okay to use some kind of software to solve a system of equations. Just tell me you would write, used Wolfram Alpha to solve the system of equations. Or even here, when we solved our characteristic polynomial. Perfectly fine, just tell me how you did it. This is still showing your work. Like everything you see me write here is what I would consider a complete solution. Okay, so this one, just a word of warning here. Something funky does happen here. We get a repeated solution. So be on the lookout for this one. This one's going to be a little tougher. And I will find what's going on with this, why the help video is not attached, and I'll fix that. Okay, we do have a group assignment that's coming up that always causes a bunch of trouble. Decoupling a system. I want to quickly talk about. This due, that's due in about a week. Okay, so you got to make a bunch of substitutions. Our goal here is to get an equation that has u1 double prime equals a bunch of stuff that only has u1 in it. And u2 double prime only has u2s in it. So that we can just solve each second order DE independently, then go back and solve for x's. So I've told you what substitutions to make here in order to make that happen. And it's a good bit of algebra here. So these two equations here and these two are identical. They mean the same thing. They're just worked backwards. You kind of will have to use all four of these at some point. It's a whole bunch of algebra. So here, let me maybe get you started on this. So we're given 3, 1, 1, 3. And we're told to use these substitutions. I know that we can use these substitutions because I've worked the problem out ahead of time. By the way, you could do these in the other order and it still works. Or I could make this x2 minus x1 and it still works out. These were just the ones I chose that worked out the best, I think. So u1 is the difference and U2 is the sum. And then what's going to be helpful is solving these two for x1 and x2. That's already been done. X1 is the sum, x2 is the difference. And I got to make sure I wrote that in the right order. I think so, yeah. Okay. So I could take, say, this equation right here. Here's one way I could approach this. I could take U1 prime and just distribute here. That's going to be x1 prime minus x2 prime over 2. I know what x1 prime and x2 prime are. They're right here. So plugging this in right there, I'll get 3x1 plus x2 minus, now I'm going to subtract all of this. So I'm going to have to distribute that minus an x1 minus 3x2. And that's all over 2. So what do we get there? U1 prime equals, looks like I get 2x1 minus 2x2 over 2. That's x1 minus x2. But that's double this guy. That's going to be twice U1. So I'm halfway done. And I realized as I'm writing all this, these are all double primes, not primes. Every one of these primes I've written is a double prime. This is a second order. Even these are double prime. Wait, what? Yeah, those are double primes. Which is why we have to go through this, because we don't have tools for solving second order systems. So if we couldn't decouple it, we wouldn't know how to solve this. So let me make sure that's right. Yeah, if I take twice this, yeah. Okay, so there's U1 double prime. I know how to solve that. Like that is the DE U1 double prime minus 2U1 equals 0. It's a second order linear homogeneous with constant coefficients. And we assume U1 is e to the lambda t. U1 double prime will be lambda squared, e to the lambda t. We get our characteristic polynomial. Like I'm kind of doing most of the problem here for you. We get lambda squared minus 2 equals 0. Lambda is plus or minus square root of 2. So like we're almost done solving U1 there. Play a similar game, find U2. You'll get a U2 double prime in terms of just U2, just doing some substitutions. Then once you get U1 and U2, once you get both of the U's as solutions, at the end it asks you, now go back and give me x1 and x2. So x1 is just the two you got added together, and x2 is them subtracted. Okay, hopefully that's enough. I kind of did a quarter of it for you there.